So here are assignments that are coming. Oh, look at these. Desmond rational function, April 27th, today. I'm flexible with due days. This, when I put it, felt like a long time ahead of us, but now it's due. And then the next one, which would be hopefully finished by this weekend, and then shoveling the driveway exit ticket is here. So please uh, don't don't think that we're not doing that. All right, so let's talk about what we are doing today. So today, we're already day 14, and, oh, not yet. Okay, here we go. Suzanne, do you see day 14? Okay, and Annie, I see Annie, Stephen, and okay, so here's the plan for today. Uh, oh, where are the recorded classes? Slowly but surely, I uploaded 2 classes. Hopefully, I'll catch up. Editing takes time. Editing videos takes time, and I want to make them short. So I uploaded 2 classes, and I will be uploading, hopefully this week will be current. And now we're going to do another Jamboard because I think that was a hit. And if you haven't done a Jamboard with us, we're going to go over the rules in a moment. And it's a which one doesn't belong. And then we're going to talk about it, of course. We're going to do the review of the quadratic functions. We already talked a little bit about, or a lot, about the reciprocal of linear. And that would be on the previous class, which would be uploaded hopefully today or tomorrow. Then you kind of will have time to work on pending assignments, and we'll have time for Q&A about the assignments that you're working on. And that would be it. Okay, so let's see. This is the which one doesn't belong, but we're not going to do it this way. What we're going to do is this. For those of you who are new, or who haven't new to the Jamboard, don't do anything just yet. A Jamboard is this. It's just a kind of a collective place where we come and share stuff. Karen, very patient. Thank you for being patient, Karen. Really appreciate it. Okay, she's there already. So you'll be put in random group, just like we did in class, and this is a which one doesn't belong. Karen, can you just wait a bit for your partner to do some thinking? You don't even know who your partner is, so be patient. And basically what you can do is you can write using a pen here of different colors, different thicknesses, so you can do stuff here if you want, right? If you want to draw, if you want to erase, it's kind of cool. And also you have these sticky notes that you can make notes here, right? Right, and so when you save it, this comes here and everybody can see it, okay? Now, this is very democratic, and that means that everybody goes into it. Everybody can see it, and everybody can edit it. So this is an exercise in trust, and it worked fantastic last time, and I'm optimistic that it will work again this time. But here are the a bit of the rules. You're going to be placed with a random partner. There's a link to the Jamboard. You can come and get it whenever the time is right. I only want you to go to the page that you're assigned with your partner. And of course, you know how the which one doesn't belong works. Give me a reason for each. Maybe take 2 or 3 minutes to do it on your own first. Then go to the Jamboard, okay? And then we're going to debrief. So before we do anything else, well, we need our random groups, don't we? The Jamboard link is on our front page. Be careful. Is this the first announcement here, day 14? The link is right here where it says Jamboard. Yeah, and I'll see you there. This is group 10, who is Sarah and Karen. So I let you tell us something about your answers, either of you. And you can unmute yourself, right? You know how to unmute yourself? Okay. Okay, Sarah, you're not mute anymore. And Karen is going to become also.
So we said that our first diagram, or our first function, it only touches 2 quadrants, meaning that it's all positive, and we don't have a diagonal asymptote, which means that like its asymptote is just vertical, like the 2 parts of the function are touching each other, sort of. Our second function, we had doesn't pass through the second quadrant, so it's only in the first, third, and fourth one. And then it has the only negative vertical asymptote, so it's not at x equals 1 like the other ones are. And it's the only function that goes into the third quadrant. The other ones just stay outside of that. Our third function, the bottom left, is possible horizontal stretch because it looks sort of more spaced out than the other 3 functions. It goes through the origin at 0, 0, and its horizontal asymptote isn't at y equals 0, it's above that, and it has the lowest y intercept. And then our last function is the only negative one, so it's sort of oriented a different way than the rest of the functions, and it's always increasing except at the vertical asymptote, and it is mostly in the second quadrant.
All right. So if you were in the class, we would give you a clap. So we're going to give you, I guess, a virtual clap for that, Karen. I do have a couple of comments here, though. There's a couple of observations I have. When you say no diagonal asymptote, none of them have a diagonal asymptote, okay? I can understand that somebody might be thinking that, say, the reciprocal of this function does something like this, right? A straight line here, or here, or here, right? But those are not asymptotes. That would be the reciprocal, which is it's a linear function. It's not an asymptote, right? So let's just clarify that technically, and I'm sorry to erasing the numbers, technically the none of them have diagonal asymptotes, okay? So I don't know if that was that misconception of the diagonal asymptote. So this technically is inaccurate. Okay, the rest are pretty good. The other observation I have, and I commented on this last week, and I see these happening a lot for reasons that I still need to understand, but it happens, is this one. Okay. There is no such thing as a negative function. We use this term, we were using it in polynomial functions when we meant negative leading coefficient. I'm not sure what this means by negative function. I'm going to think that perhaps you're thinking that the reciprocal does this, right? And because the reciprocal does this, it has a negative slope. Arguably, the linear function has a negative leading coefficient, but the function itself is not negative. The function technically is negative here, right? And is positive here. So there's no such thing as a negative function, as it were. So please, this terminology, we need to clarify because it seems it's very pervasive, and I don't know where it comes from, but I see it every year, and I see it often. So I'm just thinking, keep that in mind. The functions themselves are not per se all negative or all positive, right? At some points they may be negative, right? So other than that, nice. This is the lowest y-intercept at the origin. That is true. Okay, so nice. And we're going to go, there was another one that I wanted to see. This one. Okay. Let's see here. No, this one, team 5, which was Malcolm and Andrew. Okay, so I put a comment on them for this one. Andrew, would you like to give us a tour of these answers, please. Is Andrew here? There he is. But we can't hear you. Is your volume off? Can Malcolm and Annie and Mark, can you hear Andrew?
No, I can't hear him. Can you hear me?
I can hear you, but hold on, let me, he was mute and I'm trying to unmute him, but for some reason it's not working. So Malcolm, would you take over, and then when Andrew is ready, he can come in?
For sure. I think that Kieran kind of summed up what we had already, what we had already put down in ours, just in different terminology. Top right function is the x. It's the only one where x is a positive value. In turn, it's going to be a negative vertical asymptote. All right. The bottom right, the sign of the function is the only one that's negative. We got that one as well. And the bottom left, it's the only one where the horizontal asymptote is above the domain. And in the top left, I had some issue. I thought that was a quadratic rational, but you'd clarified that with your comment.
Well, let's talk about that one. That's the reason I wanted to show these to everybody. I think you were onto something. This function, the way it is not a quadratic. It's obvious it's not. However, I think what you were trying to get to, I don't know if it was Andrew or Malcolm, was that this is the only one that is a reciprocal of a quadratic.
Yes.
Yes, it's not a quadratic itself, but it's a reciprocal of a quadratic, right? So just like we did before, this one does the reciprocal, but this one, the reciprocal is just not linear, right? So we're going to talk a little bit about those today, but you're on the kind of on the right track. Again, this idea of the sign of the function, you need to refine that language because it's a little confusing, okay? Or it's not accurate, not about the confusing bit, but the accurate bit. Okay, so I'm going to go to group 1, which has John and Justin. So be prepared, my friends, to share anything here. Here you go. Either of you can tell us what some of the ones that you did find. No. John, you have the con, you have the mic. And where's Justin? Oh, did he leave the room? Oh, there he is. Who's that?
Justin.
Yeah, we can hear you, Justin.
Okay, so for the quadrant 1, I put that 1 because the end behaviors are made to be different. And then it does not touch the negative half of the y-axis compared to the other ones. I couldn't think of any for quadrant 2. And then for quadrant 3, it's the only one that goes through 0, 0. And then 3 because the y-asymptote is not at 0. And then for quadrant 4, we had that sticky coefficient for the graph.
Okay. All right. Thank you, Justin. Let's talk about these comments that you have here for the first one. End behaviors are different from the other. Let's talk about the end behaviors of this. When this function goes this way, as x gets bigger, this function approaches 0. Is that correct?
Mm-hmm.
And when it goes this way, as x gets very, very, very small, this also approaches 0. So the end behaviors are the same. The function approaches 0 irrespective of x, when x gets very, very big or when x gets very, very small. Okay? And I think the same is true for this one. Let me put it in maybe in a different color. The same is true for this, right?
What about the M behaviors for Y?
That's a good question, Justin. And I'm glad you asked it. Thank you. N behaviors refer not to what happens to Y, is the N behaviors is what happens to the, well, what happens to the function when the values of X get very, very small or very, very big. So what we're looking at is the values of X, but what impact does that have on the values of Y? So when we look at N behaviors, it's always at when X is very, very big or where X is very, very small. Every time we talk about N behaviors, right? What we can say here, for example, is that as the function approaches 1, right? Let's take a look at it for a moment. As this function approaches 1 from the right or from the left, let's see, when this function approaches, when X approaches 1 from the left and from the right, the function approaches positive infinity, yes? But that's not an N behavior, right? N behaviors literally are at the end, as it were. I don't know if it's a bit strange, but that might help us understand it. Way when X is very, very big or when X is very, very, very small. When X approaches negative or positive infinity, right? Not when X approaches 0. Okay, I hope that clarified it. Justin, if it did, can you give me a thumbs up with from the reactions at the bottom of the menu? No, or you can just tell me if that clarified it.
Yeah, that was good. Thank you.
No, thank you. Okay, I really appreciate when people ask questions because it helps all of us. So good job there. So yeah, I'm glad. N behaviors here are a bit tricky. Okay, so let's see here. Who would like to? Let's go to group 6 very quickly, and then we'll do maybe 1 or 2 more. Group 6, which Stephen and Inalua. So who would like to take the mic? Okay, Stephen, you win.
All right, lovely. So first things first is I have a wicked partner, just saying. Secondly, so in the first chart is I guessed that it was quadratic. Just based on like the actual shape itself. So I just wanted to throw that one out there. Otherwise, I feel like I'm really just going to repeat myself from all the other examples that we talked about earlier, but the one thing I think we have different from everyone else is the first graph, it's got a line of symmetry in it, where it can be symmetrical. The fourth one, I know you clarified this earlier, but I think it's because the direction it heads in, it feels negative to me, but I do understand that you cannot technically have a negative function. Otherwise, I think everything is very self-explanatory. Like the second one has a negative X asymptote.
Asymptote, yeah.
Thank you.
Easy for you to say.
The third one crosses, the only one that crosses the origin.
Yeah. Okay. All right.
I just have a question.
Yes.
So you said that there's not really such a thing as a diagonal asymptote, right?
No, sorry. No, that's not what I said. What I did say was that none of these have a diagonal asymptote. There are instances where we have rational functions with diagonal asymptotes, but we haven't talked about them yet in Alua. But I'm not sure if I'm answering your question.
Yeah, you are. I see it now. I did make a mistake. They don't have a diagonal asymptote.
Yeah, no. There are functions. Imagine that we had sometimes we have something like this, and we have a function that does quirky things like this and like this, right? So these would be a diagonal asymptote, right? But we haven't talked about those friends. Technically, in our course, we don't talk about them. They're not in our curriculum, but you occasionally have functions like these. They're very cool, but that's a diagonal asymptote, but we haven't talked about them yet.
Okay.
And maybe, yes, I hope, but thank you for asking. That was a good one. Okay, I don't know if any other team has something that is unique that you want to share. I'm seeing group 4. I like their diagrams. I can't follow them, but I like them. So Emma and Keisha, maybe we'll give the last word to you, friends. And if there's anything different, can you share it with us?
So basically, I don't know if this was already said. Can you hear me?
Yeah.
Okay. There's a lawnmower outside. But we said that the top right graph was the only function that didn't have a vertical asymptote, or the only one that had a negative vertical asymptote. And we kind of just went back and forth about that. That's what all on the right, because some of them, since we don't have like exact values, some of them look like they could have a vertical asymptote of more than 1. But we just said that it's the only one that has a negative one because we don't have the values. The top left has it kind of looks, it's the only one that's symmetrical, like at the vertical asymptote. It's the only one that doesn't, it's the only one that touches 2 quadrants. Yeah.
Good. I do like this observation you just made, Keisha, about the negative vertical asymptote here, right? Because here, you're right, I love you drew it. These, if we had to write the equation for these, it would be x equals like, I think 2 or something like that. These might be x equals 1. These would be x equals -2, right? And then these one may or may not have an asymptote. Actually, I don't think it does. We'll talk about this in a little bit. So this is the only one with a negative asymptote. Now, I'm not sure we have heard that before. So that's kind of cool. Now, as far as symmetry goes, this is interesting because technically they are all symmetrical. If you look at them, just the line of symmetry is different for all of them. These one, we could think as a vertical line of symmetry, but the other ones, you can think they have a line of symmetry this way and this way, right? If you kind of were to put a mirror or fold this, let me, Steve made a funny face. Let me see if I can illustrate this better. Imagine that we draw a line like I'm gonna try to draw, and that we can fold, if it was paper, and we can fold this function along that line so it lands on itself, as it were, right? So you can see that there's symmetry there. And the same thing if we drew a line this way, right? You see that? If I were to fold it, it would literally fold onto itself. Okay, so a lot of good thinking here. Thanks for coming along to the Jamboard. And I need to mention something to all of you because that is important. At some point, you are going to get an assignment. One of our summatives is going to be for you individually, to create a which one doesn't belong. Okay, and we may give you a topic, or you can choose it. I mean, maybe I'll put some topics and people can pick, but you will be designing one of these things, right? Which is kind of fun. And we'll talk about it later, what the criteria will be for us to determine which one doesn't belong, works better than others, okay? But just, I wanted to mention that to you because that's gonna be upcoming. All right, so we're gonna go from here directly, I believe, to here. to here to here. Okay. So we talked about the graphs of the reciprocal of linear functions, right? Things like this. Well, if we had x plus b, and then we had something like this, 1 over x plus b. If I were to type it nicely, no, I didn't. Right? And then this is the type of thing we were talking about, right? And we establish a number of things here. There's a connection between these two functions. I'm going to summarize it very quickly. If I have my linear function, which is the green one, my y-intercept, let's say the y-intercept there is at 1. I'm going to change these friends so my numbers are friendly. I'm going to go from -5 to say +5, and let's go by ones. Okay, so I can see here, for example, the y-intercept of the linear is at 2, and the vertical asymptote for my reciprocal, actually, no, the connection is here, not here, is the x-intercept. The x-intercept of the linear produces the vertical asymptote for the reciprocal. So if I move the line a little bit, and now here, the x-intercept, not the y, in this case, because the slope is 1, they are the same, but I can have a different slope. And the x-intercept gives me where my vertical asymptote is. So that's the connection between these two, one of the connections. The other connection that we talked about is this. When the linear function is increasing, which is always, the reciprocal is decreasing. Yeah. And this is the part that sometimes people have difficulty grasping. When the linear function is negative, the values here, if I take a look here, look at the y values, yeah, -1.28, -71, -0.56, etc. The values of these function are negative. The reciprocal is also negative, which makes sense. We're dividing a negative number by 1 by a negative number is going to be negative. So the sign of both is the same everywhere except here, because here we have an asymptote. But wherever the linear is positive, the reciprocal is positive. Whenever the linear is negative, the reciprocal is also negative. Okay, so that's a brief tour of what we did before. So what we're going to talk very quickly, and this is the next Desmos that some of you have already begun to work on. This is the reciprocal of a quadratic, and these ones are, I like them because the curves can be very interesting. So we'll do a quick overall review, and then we'll come back to see if anybody has questions on this, and then you can go and work on the Desmos. Okay, so let's first look at our quadratic. Here's our quadratic, right? And I have here a slider. So right now, my function technically is x squared minus 4, right? So I know the y-intercept is at -4. And take a look at these. Look where the intercepts or zeros are. -2 and +2. So that's a quadratic that we know and love. It's shifted down 4 units, and it's symmetrical, blah, blah, blah. Okay, now let's see the corresponding reciprocal. Please notice the way this is written. It's not 1 over x squared minus c, but the whole expression is under the, is in the denominator. Okay, ready? Here goes. Oh, look at that. Interesting. So let's talk about, for a moment, about the connection between these two functions, okay? And let's compare what we did just a few minutes ago with the linear. Let's first talk about what happens with the signs, positive or negative. So I'm gonna hide the reciprocal. And here, the sign of my quadratic is positive. Take a look here. You see how the values 8.18, 7.59, and so on and so forth is positive, right? In other words, it's above the x-axis. The quadratic is positive here, and it's also positive here, right? Here is not positive, it's negative, right? Look at all the values, the y values are always negative, right? So my quadratic is positive, and then here has no sign, it's 0, then it's negative, then it's 0 again, and then it's positive. Let's look at what happens with the sign of the reciprocal. Over here, I mean, it's approaching 0, but it's not 0, so it's positive. Yeah, look at this. It's a very small value, but it's positive. And as I move here, it stays positive all the way up to, I don't know where, the positive infinity. So when these guys positive, the other one is positive too. And here, the same thing happens. When the quadratic is above the x-axis, so is reciprocal. It's also positive. It's getting smaller here, but nonetheless, it's always positive. So the signs are the same. Same thing here. Here, everything is negative. We can see it, right? The only tricky part is what happens at here. Take a look at here. And this is kind of interesting. We have, excuse me, we have a minimum for the quadratic, right? And guess kind of what happens to the reciprocal. It has a local maximum, which kind of makes sense because here we are dividing 1 by -4, which is going to give me here -0.25 or 1/4. And that is the biggest possible value I can have in this place, right? When the function is negative. It's a local maximum. Of course, here is bigger than -1/4, but in this interval, in this space. Cool. So the signs are the same. Now, what happens with intervals of increase and decrease? Please, these are connected, but they're not the same. So we only talk about signs. Now, let's talk about intervals of increase and decrease. This function is decreasing from when x is -infinity all the way to here. Yes? It was always decreasing. It was getting smaller all the time. Look at it. From 9.6 to 7.4 to 2.1 to -2.7 and all the way here to -3.9, and then it became it was decreasing. It got to a minimum, and then now is going to be increasing. Yeah. So this function decreases from -infinity all the way to 0, and we always look at the values on the x-axis. From -infinity to 0 decreases, and then from without touching 0, and then from 0, when the function x is greater than 0 to +infinity, the function increases. All right, what happens with the reciprocal? Let's look at it. When our quadratic is decreasing, our reciprocal is increasing. They're opposite. The intervals of increase and decrease are opposite. The signs are the same. And that, I know I repeat it, and I apologize for repeating so much, but it's a point that people confuse a lot. Now, here, this function kept decreasing all the way here. Meanwhile, our function here kept increasing. Even though it disappeared here, guess what? When he came back after the asymptote at -2, when he came back here, it was always increasing. Look at it. yeah, is getting bigger and bigger and bigger. And then here reaches up a local maximum. And just when this guy increases again, our reciprocal decreases. So those are the key ideas that I wanted to share with you. And those are kind of the key ideas that you will be working on in that Desmos. So it's kind of a mini lesson. And the other part that I want you to notice is this. Right now, C equals 4. And look at where we have our x-intercepts, -2 and +2, right? So if I were to make this equation x minus 4 equals 0, I would have the positive and negative square root of 4, which is -2, +2. If I made these 3, take a look what happens to the roots. -1.732 and +1. This is the square root of 3. Yeah? You see that? The square root of 3. And if I was to put it at 1, this is going to be positive and -1. The square root of 1. Positive and negative, right? So I don't want to spoil it for you because there's some stuff that I want you to see. The only thing I've done here is make C positive. Interesting stuff happens when C is 0. Take a look. And interesting stuff happens when C is negative. Ooh. But I'll let you explore that in the Desmos. The key ideas that I wanted to share with you are the signs being the same and the intervals of increase and decrease being opposite. And I'm going to stop sharing. And